And the very first lecture I talked about why we need to do statistical mechanics. It's a difficult subject, very difficult subject, and in the evolution of statistical mechanics, physicists and chemists almost, they were hand in hand. Many things were done together. Willard Gibbs many times is one of the father, was considered to be a chemist. When I was doing PhD, he was referred to as a American chemist. Now I think physicists claim him as much as. So very first lecture that we did the preliminaries. These we talked about how if you take a undergraduate physical chemistry or even MSc level physical chemistry book, what you will find is that the chapters except the wave mechanics, 1 or 2 chapters and spectroscopy, if there are 32 chapters, you will find 20-25 chapters are things like kinetic theory of gases, thermodynamics, entire 3-4 chapters of thermodynamics, then you have a phase equilibrium, then you have a phase transition, then you have binary mixture, you have solution, electrochemistry. All these chapters that you study, they are all, and remember that when you study of conductivity of the ions, lithium, sodium, potassium, then you plot it against the size. They are supposed to go as 1 over size of the ion, crystallographic radius, but it just goes, instead of going like that straight line, it just goes the maximum and falls back. That if you remember, that was called conductivity times viscosity is called Fulton product, and that non-monotonic behavior was called breakdown of the Fulton product. The reason I am talking of the breakdown of the Fulton product is that because I want to make a point, and a very important point, which is the following. So, this is limiting ionic conductivity in electrochemistry, you have read d by Huckel, remember, and viscosity and 1 over r ion. Since this is nothing but the what is called the diffusion, and diffusion is inversely proportional to viscosity. So, this product should vary as 1 over r ion, which is like this. Instead of that, what happens that it just comes down like that, and this lithium, then sodium, then potassium, it goes like that, and this is here where cesium, rubidium and all these guys are. Maybe the potassium will be a little bit closer to that. Now, so in the undergraduate textbook of Castellan or Moore or Gladstone or all other Atkins, they call this breakdown of Fulton's product and give to some pictorial description like iceberg formation around the small ions. So basic idea of my telling this is that in much of physical chemistry in undergraduate, whenever we have anything interesting going on, we have a picture that came, but that picture was mostly very approximate. However, behind all these pictures there is a quantitative theory that was largely developed in the post 1950 and or maybe 1960s, 70s, and aided enormously by the computer simulations. So, statistical mechanics has come of age now, and like in quantum chemistry, you have all the packages. So, a student working in a quantum chemistry laboratory, they can always have these packages, and they use these packages, for example, doing organic chemistry calculations and other things. Statistical mechanics, those kind of packages are just coming now in terms of Gromux or Amber or the different force fields that have come. So, it has become much more institutionalized now. So, there are a lot more calculations going on, and it has played a very important interesting thing that it has gone again okay, it's a rapidly developing field, huge amount of it's not that much visible still in India, though there are now significant number of people doing stat mech in chemistry. Physics always is a huge in physics. So, this was the preliminaries that I explained that why that you need to invoke statistical mechanics to understand the what we call the large scale phenomena. Large scale phenomena, many particles like phase transitions, like this conductivity, or understanding thermodynamics, or, so phase equilibrium, phase transition, all these things. We discussed that in the first lecture. Second lecture, we had little bit of mathematics where we did probability and statistics. And because this name is statistical mechanics, which combines mechanics, mechanics is very deterministic. It starts with Newton's equation, and so everything is initial conditions given, you can predict the future. But as I told you that unfortunately we cannot even solve what is called a 3-body problem. Even if you have 3 particles, we cannot solve that analytically. Even 2 particles having a little complicated potential, not even complicated, radial potential, say Lennard-Jones potential, even that has to be done through a quadrature. So the whole A of so this is a interaction between A and B, R A B. This is the Lennard-Jones potential. We call it 612 potential. The form is, this is a universal notation, sigma R by 12 minus sigma R by 6. Let me say A and B are the same 2 particles, both are A, then I do not need the B, I can do without this index. There is a separation between them, that is R, and this is the form. It very important to understand these things, the interaction potential between 2 particles. When they come from a distance, they attract each other, but when they come too close, electrons overlap and there is a huge repulsion. This simple potential, apparently simple potential, plays a very important role in the understanding of many phenomena, solvation, phase transition, many things. However, coming back to the point I am making, even these potential in a 2-body we have to do by quadrature, and by the time I go to 3-body potential, if I bring one more, I cannot solve the Newton's equation anymore. Okay. However, when you think of the properties of water, then you think of properties of water in a glass which has Avogadro number of molecules, and they are strongly interacting, and we cannot use Newton's equation anymore to solve them. If we want some really very complicated and sophisticated effect like polarization, that one molecule is polarizing another molecule, then we have to do quantum mechanics, that is even more difficult. Okay. So we are faced with then a situation where we have to explain natural phenomena like why ice melts and then why steam 100 degree centigrade becomes steam, why I put a solute there, then depression of freezing point and elevation of boiling point, that you have learned in school. And these kind of things, if you want to understand, you cannot from first principles. And what do I mean by first principle? This is a term we use again and again in statistical mechanics. We also use quantum mechanics. Quantum mechanics, when you see first principles, we think that we are starting from Schrodinger equation and interaction potential and going about it. Of course, they are looking at the electronic properties, and there are approximations and there are answers. In statistical mechanics, what one can do quantum statistical mechanics. Right now, let me focus on classical statistical mechanics, that because the large amplitude, large scale phenomena like phase transition, or as I am saying, why steam bites you more than water at the same temperature, depression of freezing point, like you add salt, that is what the principle of ice cream, that you get, you can go to minus 20 degree centigrade, that is where ice cream forms. You can do that experiment doing that. Now, you can ice cream maker, and there is a liquid there which is goes very low temperature, and you put water and you can make the ice cream. No, not water, milk and water. Now, so these many large amplitude phenomena that we want to understand, we cannot do by following Newton's equation anymore. So then we need but how do we go? So Newton's mechanics, classical mechanics means Newton's equations or Hamilton's equation or whatever. Let us continue with Newton's equation, which we know Newton's equation then is not going to help us, because we cannot even solve a 3-body problem. That is where the statistical mechanics comes in. It was formulated starting with Maxwell, Boltzmann, then Willard-Gibbs. Now, so what is then I do? I cannot do mechanics as I know it. So I have to do that. This was a huge conceptual and philosophical problem in the end of 19th century, when people started introducing the concepts of statistics. And it all started with the work of Maxwell. You know, all of you know the Maxwell velocity distribution. Maxwell is the first guy who told, okay, if I have in a glass jar a bunch of atoms and molecules at a temperature T, I do not need to follow at each properties of each atom or molecule. Instead, I can talk in terms of a distribution. So Maxwell said, okay, and Boltzmann also, what are the properties we want to know? I want to know the viscosity of the gas and later viscosity of the liquid. I need to know the pressure, equation of state, how is the PV equal to nRT is the ideal gas. But when you go to little high density, ideal gas law breaks down, and then comes the virial equation. Okay. How do I get then virial coefficients? So, so then Maxwell said, I don't need to know individual atoms and molecules in a striking departure from classical mechanics. Instead, I'll talk of a probability distribution. As soon as the concept of probability distribution came in, then came the question of statistics. How do I define probability? I need statistics to define probability. Okay. So that is what it was the second lecture, and which we discussed probability and statistics. Then the last lecture, third lecture, we started talking the postulates. So fundamental concepts and postulates, I'll revise a little bit of that, but then I'll not do Liouville theorem in this lecture, I'll do it later. I'll go directly to something which is little bit more application, ensembles and partition functions. And these are from my book, and what I written there, that actually earlier I have this from postulates to formulation. So we'll go to the formulation of statistical mechanics today. So it's a very important class in that sense, this and next class. And what I had before the title is that from promises to realization, because there was this promise that was made by Boltzmann and Willard-Gibbs. Well, Willard-Gibbs mostly realized it. So the postulates, both Boltzmann and Willard-Gibbs played a role in giving us the main postulates of statistical mechanics. From there, we'll directly go now, because this is more to do with dynamics, and we'll do that at some stage, but not now. So the postulates, there are two postulates what are connected by the one hypothesis, and based on that, statistical mechanics promises to explain the natural phenomena, which is a very high A. So first postulate, so there are postulates that I did last, but this is so important, it's no harm done doing it once more. So first postulate is called time average and equal to ensemble average. And second postulate is called equivalent probability. And what is not told in not any book is that why we need the hypothesis, and these two are connected by Ergodic hypothesis. I'll spend next 5 minutes talking about it, then we'll go to the starting the partition function and ensembles. How did that come? It came because Boltzmann tried very hard to develop a kinetic theory of gases. So, when you read the, I mentioned this last time also, you know, like in Schrodinger equation in quantum mechanics, if you noticed, I did not notice, but I realized later, partly because of a book I picked up in 1.5 rupee in Presidency College, the old books next to Presidency College, that fence, that when you study quantum mechanics, see all the way from hydrogen molecule, you do not have any name, you know, there is no name, because particle in a box, rigid rotator, harmonic oscillator, hydrogen atom, hydrogen molecule. That because everything was done by Schrodinger alone. You know, when he first hit upon the idea, he went to a resort area and stayed 3 months there and solved everything. So, the whole quantum mechanics, as you read in MSc, you know, is just done by one man. Similarly, kinetic theory of gases, again there is no name. Almost entirely of the kinetic theory of gases was done by Maxwell, and a bit here and there by Boltzmann later. So, when this beautiful paper of Maxwell appeared, there are other papers around that, but not as clear as Maxwell and also not meant to the English speaking world. Then Boltzmann fell completely in love with that paper until the end of his life. He died early, 1906, he carried that paper. And then he tried to extend the Maxwell's, Maxwell had this funny mix of assumptions that particles are like billiard ball, but then on the other hand, he is also talking of an ideal gas. Ideal gas do not interact, they pass through each other. So, there was these contradictions in all the ideal gas in our study of kinetic theory of gases. So, Boltzmann set out to extend it to real gases and separate, and there is a famous equation of Boltzmann kinetic equation. But Boltzmann did not fully succeed, he tried very hard. He could go only to very dilute gas, and he also made some assumptions which were heavily criticized to the extent that probably caused his death. Now, when Boltzmann tried very hard and could not take into account even with the, he is the first one, Maxwell had it, the probability distribution concept of probability, but he did not explicitly stated that in his formulation, and that was done by Boltzmann. He explicitly added probabilistic concepts. He said, okay, if I have a probability of a particle at a position r with momentum p, I call it FRPT. Another particle at position r1, I say these R1 P1, these R2 P2. Then I have, together I have a 2 particle distribution, like I call up F1, F2 subscript 2, R1 P1, R2 P2T. That a given time, a particle has R1 and P1, another particle is R2 P2. That is a 2 particle distribution, but it is so difficult because it has R1 and R2 all are 3 dimension, 336, and P1 and P2 another 336. What a beast it is. So, he made an approximation that F2 R1 P1 T2 this was called is random chaos approximation, and that he was immediately and hugely criticized for making this approximation, but he had no other option. Once subsequent whole century people have tried to, 100 years people have tried to extend that and have done to some extent. So, when Boltzmann tried this, he could extend only to. On the other side of Atlantic, one person who looked with concern at the difficulty faced by Boltzmann, who was equal fan of Maxwell and Maxwell distribution, his name is Willard Gibbs. Willard Gibbs then thought, okay, what Boltzmann did is not tenable anymore. We cannot go that way because we cannot do 2 particle, 3 particle is out of question, and there was many other complexity. So, then Willard Gibbs make the important observation that as I told last class also, that let me have 10 glasses of water half full. Now if I look into, by that time the microscopic motions and all these things were somewhat, kinetic theory of gases was already understood. So if these 10 glasses, all of the glasses, if I think of the microscopic state, and a microscopic state now is defined by giving the position and momentum of each particle. So I have n particles, then I give you R1, R2, Rn, I give you P1, P2, Pn, that together determines my microscopic state of the system. Now my 10 glasses, all these have water. Now all of these microscopic, all of them have the same properties. They are in same temperature, they have the, let me call the same volume, they have the same pressure, they have the same specific heat, they have the same conductivity, same entropy, every property is the same. But certainly the microscopic state of all of them would be different because there is such a huge number of microscopic states. Atoms and molecules are moving around. So then Willard Gibbs realized that if I can now have a mental replica, I have just one, this is my system in question, this is my real system. Now I mentally construct billions and billions of my mental replicas such that they are thermodynamically same, but their microscopic states are different. So they are mental construction. This mental construction is called ensemble. Then he said, okay, if I wait for a long time, then my system in question going to go through all the microscopic states, which are essentially same microscopic states which are these particles are, these systems are. So now, if I now in my mental replica, I create a mental billions and billions of copies of these things which I call ensemble, the collection is called ensemble. If I can take average of that, then that would be same if I now study what Boltzmann tried to do, study the detailed trajectories. Trajectory means the path that a particle takes, all the particles take together, that it will be the same. That means if I can do a time averaging over infinite time which Boltzmann tried, and if I can replace by the ensemble averaging over all these my mental, I will be little bit more exact because sometimes words language don't carry the difficult, but so now so that was the first assumption of first postulate of statistical mechanics, that time average equal to ensemble average. Now as soon as Gibbs did that, there is a problem came that when I am doing time averaging, yeah, I have one system which I am studying for a very long time, and I am studying the motion of atoms and molecules, their positions and momenta, and then I am averaging a property, for example pressure, I am averaging a property, for example the internal energy, their enthalpy, entropy. But now I have replaced by my mental construction. But what is the guarantee that my mental what is the guarantee that the system I am following for infinite time will go through all the microscopic states? And second, even if they go through all the microscopic states, what is the how do I give a probability to it? So that is the time he introduced that I am going to talk of the systems with a constant number n, constant volume v, and constant energy E. So all my mental replica have a constant energy E. So all the microscopic states have the same energy E. If all the microscopic states have the same energy E, then I can now assume, and I have no other option but to assume under this ensemble that there is equally probability, all the microscopic states are equally probable. There is no other option than to do that. It turned out, it is correct, it worked out, but that means all the subsequent work said that is okay. All the microscopic states with equal energy are equal. We will still work on this. So these are the two first postulates. First postulate was introduced the ensemble, one of the most brilliant idea that mankind has ever come up with. It probably doesn't get the sufficient credit that how brilliant this construction is. The ensemble and then time average equal to ensemble average, but as soon as this was made, he had to average over all the microscopic states and he needed a probability of being in a microscopic state, but since they are all the same energy, the natural postulate was that they all are equal probability, that is equally probability. But there are no other option, but it turned out to be okay. Now came what I was in between started talking about, that now came the problem following, or then face the following problem. Okay, I have done time average to ensemble average and I have said equal probability, but what is the, so in ensemble average I am going to billions and billions of microscopic states, but what is the guarantee that when I do a time averaging, the system goes through all the microscopic states in a given time, capital T say. What is that guarantee? Then comes introduce the constraint of the hypothesis which is called Ergodic hypothesis, which means the system indeed given sufficient amount of time, it visits every microscopic state equal likely. So first postulate required the second postulate because to average over ensemble, and once this is set in, but then I have to make sure that my system visits every state. So this is then made the Ergodic hypothesis which connects these two hypotheses, these two postulates. So this is the very important point of the statistical mechanics, and why it is important? Because armed with these two postulates and one hypothesis, that is where everything, whole of statistical mechanics is built on. It is amazing, you know. This is what you can say equivalent to, there is no equation, equations will come later. It is the equivalent to, you are saying that okay, this is a wave function and the wave function has to have these properties, satisfy Schrodinger equation, psi square has to be positive and co-square integrable. There are similar kind of things that comes here in this the statistical mechanical formulation. This is very, very important to understand this part. It is more important now to understand than before, because when we do now, as I was talking you a while ago about the different packages, time average is the what we call now the molecular dynamic simulation, and this is ensemble average, what is called Monte Carlo. So these are the two major branches of computer simulations that we do. And the same problem envisaged by Gibbs so many years ago, more than 100 years ago, is exactly the problem we face now. So when I do equilibrium statistical mechanics, equilibrium properties like phase transition, I land up the problem by one phase to another phase. That cannot be done in molecular dynamic simulation because it cannot explore all these states. It gets stuck in a minima. We will talk about it. Now, that is where you go to Monte Carlo, which is much better to do time independent equilibrium properties. Now, Subhasis was asking me today why we do mix these two. The reason we mix the two is that many times molecular dynamics gets stuck. So we follow a hybrid where you start with a multiple, not too many, maybe 10 or 20 initial condition, then do molecular dynamics on that, and then probability of initial state given by the energy. So the hybrid simulation is a very popular thing now to study really complex problems, like in biology or like in water in a supercooled in a very low temperature. There are a lot of interest now in water in low temperature because there is some presumably liquid transition and people have gone banana over that. Okay, so But now I will slightly talk, if I have. Okay. Now this is the kind of thing that I want to point out. Say I have a particle which is undergoing some kind of a, so this is a particle, but I have a kind of a landscape, energy like this. In that case, the particle can get stuck here. This is a very simple thing, a one dimensional walk, random walk, but in ordinary random walk, drunkard's random walk, you don't have the, you have a flat energy, but you have a we call rugged energy landscape. Such a simple problem, one dimensional with the energy distribution, it just hell to get a molecular dynamics simulation going into this kind of a system, because it becomes non-ergodic very quickly. And so if you want to calculate equilibrium properties, you do a Monte Carlo, you just sample, that is very easy to do. On the other hand, if you want to do dynamical properties, it becomes very, very difficult. So this is an example what we call compromised ergodicity. So the ergodic hypothesis was particularly made to make sure these kind of situations are not done. Now, why it does not is less serious, many of the cases in NVE, because all of them are same energy, like this will be ruled out by, if I can do the simulation NVE, because these kind of things are not allowed. However, in real system we do not do NVE, we do the other ensemble, which I am now going to discuss.